Good morning. I want to tell you about periodic potential and energy bands. So last time what we did was to take the electrons in solid as if they are like a gas, and then we did quantum mechanics with that gas, right? And I promised that the next best thing we can do is to take the free electron gas and put like a periodic potential. That's what the solids do, because almost all solids come with a perfectly crystalline structure, and we have to take that into account. So the goal here understand free electrons as we did last time plus periodic potential. So this periodic potential could be weak or strong. So the way we'll deal with is general and quite powerful. But typically in some textbooks, people can also consider weak potential because it may have like advantages in certain equations. And the result from this analysis, we'll see the change is dramatic. So you'll see that free electron picture is going to change almost completely, and we are going to have like a complete new paradigm. So the details of potential, whether it's like Coulomb or like some screen Coulomb, is actually not important. So all we need is the symmetry, and I want to spend a second hour to talk about symmetry. So symmetry, in this case translational symmetry, is important. There is like a specific way we deal with symmetry in quantum mechanics, and we'll see that in the second hour. And there are like basically two models every textbook has. First one is so-called Kronig-Penney model, and this one is kind of like what we had. It's like a, if you want, it's like a barrier, or if you like a valves, you can also think about valves, something like that, and you just repeat this. Something like that. This is a periodic potential, right? So this is, I don't know, let's call this length A, this is B, and I don't know, the barrier can be like as high as V naught, and the problem is just to solve Schrödinger equation in such a given potential. Okay? So this can be done. I want to make it a little bit pedagogical choice and leave this as an exercise. Once you get the ideas I'll show you in this course, you can also easily manage this problem. The second and a little bit more friendly model is so-called Dirac-Cohn. And in that case, rather than this potential, we are going to have like these delta functions. And they just repeat. I only draw 4 or 5, but imagine they are repeated infinitely many times. And this potential has only one parameter, right? So this V of x is like, suppose this one is just alpha delta of x. By translating this infinitely many times, I can generate all of these. And the way we do it is like, there's like some j times. Let's call A to be the spacing between these Dirac functions, and we need to sum over all j. So this distance is A, and strength is some alpha here. See, we have to deal with 2 parameters in this choice. We have to deal with 3 parameters in that choice. Good. And our task, as always, is to solve Schrödinger equation. So in the Schrödinger equation, we need to find the wave functions and energies, and we'll see in a little bit. This is going to have quantized energies, but they are going to be bands of quantization, and there will also be forbidden energies, and we are going to call them energy gaps. And the key about this problem is, so here this V of x, as you can see, V of x is equal to V of x plus a. So this is the key symmetry, right? And symmetries are very special quantum mechanics. We are going to touch upon it carefully in the second hour, but it's like a much bigger subject. So when you consider this, what we are going to find is like there are 2 things. So if you remember, we need the differential equation and boundary conditions, and in this particular symmetry we have like a special kind of boundary condition. I'll write it in this lecture, I'll use it, and in the second hour I'll prove it. So the first one is so-called Bloch condition. So this is the tricky one to understand. We'll spend some time on it. So naively, you would think, right, psi of x, because V is periodic, Hamiltonian is periodic, you would think this is also periodic, right? That's generally what people think. But what happens is actually there is an additional phase factor, like let's call it like e to the, I don't know, e to the phi, right? And the phase factor, because it's unity, we know like the norm is going to be the same. So observables should not know about this translation, right? Like in the lattice, if I put you here or here, you would notice nothing, because all your observables would be identical. And that's also the statement on the density. But wave function is not observable, and there's like an overall phase degree of freedom. And from the Bloch theorem, we are going to see there will be a special quantum number for this q, and typically we write it like q times a. Okay? So this a is the lattice spacing, and there's like a new q which should be determined from the solution of this equation. So this is the first condition we will use when we solve this. And the second condition is periodic boundary conditions, or sometimes technically it's called Born von Karman periodic boundary conditions. So this is not necessary in reality, but in solving the problem it makes it much easier, right? So we want to make it easier for ourselves, and what this means is like if you translate like n times, right, at some point solid is finite, right? At some point you are going to reach the boundary of the solid in your hand, and what this boundary condition says is like, suppose as you reach the end, you kind of wrap back to yourself, right? So that's kind of like periodic boundary conditions we used before. And this is like psi of x plus n times a. So if you do this translation n times, you come back to yourself. If you want, you can think about this like these Dirac cones to be wrapped in a ring, and you come back to yourself. That's also a good picture. So let's combine these two conditions. So I'll prove this in the second hour. For the moment, let's say somebody gave it to us and said, satisfy this condition and solve the Schrodinger equation. So let's think about this. So this psi of x plus n times a, right? By using this, if I do it one time, I'm going to get one factor. If I do it two times, I'm going to get two factors of this. But here, this condition tells me to do it n times. Then this is e to the I, q, and a psi of x, right? This condition, I just wrote this using this condition. And now I'm going to use the second condition. So the second condition says this is equal to psi of x. And for this to be true, so this thing should be 1. Right? If this thing is 1, we can say this q times n times a should be 2 pi times some integer n. And from here I found this q to be 2 pi over a n over n. Good. But okay. But if you look at this, right? So this, let's look at this q n times a is equal to this thing, 2 pi over a n over n times I don't want to look at the q times a, I want to look at q times a. So this q times a, so this is 2 pi n over n. And as you can see, if n is equal to, okay, what is n? N is equal to 1, 2, 3, 4, dot, dot, dot. But once I reach n, right, uppercase n, n over n is 1, I have e to the I 2 pi, and 2 pi is 1, and I come back to myself. Therefore, these indices, if you want, these are the unique roots of this e to the I form. So if you want, we can just only take these, and we can imagine q to be repeating itself once you go like n plus 1. Okay? So another way is like any unique root is fine. We can also take it like n, I don't know, minus n over 2, minus n over 2 plus 1, dot, 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 minus n over 2. That's also fine. I think to have like n points, we need to subtract 1 from here. So for these unique roots of exponential, what unique values of q do I have? So q is going to be equal to, okay, I'm now going to use this 2 pi over a times n over n. So if n is equal to minus n over 2, I have q is equal to minus pi over a. And if I have n is equal to minus n over 2, I have q is equal to pi over a, I don't know, something like minus epsilon, a little bit of shift. Therefore, this q is defined inside this minus pi over a to pi over a. Good. And outside, it repeats itself, so there is no need to consider q's outside this region. And this is what we call first Brillouin zone. Good. So what is saying is like in real space, x is periodic, x is some 0 to a, and in reciprocal space, q is periodic. And it is like some pi over a, whatever the periodicity in real space, you have 1 over that, just like this Fourier relation. Good. Now let's think about solution of Schrodinger equation. That's what we need to do. So here's my real line. Here is my one Dirac function. Here is another one, and here's another one. And it keeps going. Suppose this is 0, so this is A, and this is minus A. So here I have minus h bar squared over 2m d squared over dx squared psi is equal to e psi. And we know how to solve this, right? So this is, if you want, we can just do what we do all the time. So this is 2m over h bar squared, and put the minus sign here, and call this k squared. And energy is positive, so k is real. And the most general solution is a sine kx plus b cosine kx. This is the solution in that region. Good. Now we also need to solve this region, but rather than solving there, we can just use this condition, right? This condition is given to us. So let me just copy. Then this, whatever solution I found here, I can translate it to here. And the way I translate is like, so this is psi of x. So I'll write it as e to the, so I'll take this to this side, e to the minus I qa. And so this is what? So this is psi centered at x is equal to minus a, right? Think about like a function. So this is f of x. And if I want to translate it to this way, I need to write f of x minus a, so that I shift it this way. And if I want to translate it this way, I need to write it f of x plus a, right? If you think about Gaussian, the center of Gaussian is where it is, and it is like shift. Therefore, I need to put, wherever I see x, I need to put x plus a. Good, so this is like that. So this is sine k x plus a. Okay, there is also a. And b cosine, let me shift this a little bit to fit, k x plus a. Right? And that's it. We solved the Schrödinger equation. Now we need to match these two solutions, and we need to match them here at x is equal to 0. And there are two things we need to consider. So at x is equal to 0, psi is continuous, right? Psi should be continuous. Then psi of 0 minus is equal to psi of 0 plus, and this is going to give us e to the minus I qa a sine, so I put x is equal to 0 here, ka plus b cosine ka should be equal to, now I'll do the same thing here. If I put x is equal to 0, this will cancel, I'll have just b. So this is the first boundary condition. And to get the second boundary condition, we have like Dirac delta function here. We do exactly what we did for this single Dirac delta function. We are going to integrate the Schrödinger equation from minus epsilon to plus epsilon, and it's going to give us the jump in the derivative of psi. So let's do that. So at x is equal to 0, psi prime, the derivative has a jump. How do we find this? We use the Schrödinger equation. Psi plus, because I'm integrating here, I'll just write one delta function. The others are not here anyways. So this is going to be some alpha delta x psi of x is equal to e times psi of x. And now let's integrate. Integrate from minus epsilon to epsilon dx. Here, minus epsilon to epsilon dx. So this is dx. And also here, minus epsilon to epsilon dx. So this one is going to give 0 because psi is continuous. So this one is going to give me alpha times psi 0. I am using the property of Dirac delta function. And this one is going to give me minus h bar squared over 2m, right? Second derivative integrated is going to be first derivative. So this is going to be psi prime 0 plus minus psi prime 0 minus. And this is equal to 0. Or I can take this to this side and make it like equal. Or I can also write it like 2m over h bar squared. Good. Now let's calculate psi prime on the right hand side, psi prime on the left hand side. Take the difference and let's set it to here. So 1 is this. So the derivative is going to be, sine is going to be cosine. I'll have like k. And cosine is going to be minus sine. There will be a minus. And this is equal to psi 0 plus. And I'll do the same thing here. So this is the other psi. So this is, okay, this is psi prime 0. So this is psi prime 0 minus is equal to, so the derivative of sine is cosine, and there will be a k, and derivative of cosine is minus sine, and there will be a k. And now I put the boundary condition if if x is equal to 0, cosine is 1, so this is a. And if x is equal to 0, sine is 0, so this is going to be like this. And I have that condition here. Whereas here I am going to have x is equal to 0, cosine ka. And here I have sine ka. Good. And now I take the difference and use this equation. So k e to the minus I qa a cosine ka minus b sine ka minus ka is equal to 2m over h bar squared alpha psi 0, and psi 0 I can use this one. At x is equal to 0, this term will be 0, it's going to be just b. Right? So I have two equations. So this is boundary condition number 1, and this is boundary condition number 2. And I will use these two equations to eliminate one of the a or b. Yes. So this minus k. So this one. Psi 0 minus first. Oh, this one. I see. I got it. Yes, now I got it. Sorry. So this is minus. This is plus. I see. Yes, got it. Thank you. Sorry, I sometimes cannot see. Thank you, though. Also, thank you for not giving up. If you think you are right, please don't give up. That's a good thing. So this is this thing, psi plus. Okay, the other way, right? This is ka minus, and this is minus this plus this. Now this is correct, right? Let me check my notes. Yes, my notes are also that like that, and there's also k. Yes, absolutely. Oh yes. So this is plus this is minus, and I subtract this from this. Okay, now this is correct, now this is also correct. Okay. Got it. Okay, now the job is to solve this equation and the previous one. And what I will use is, I will use this equation, right, to find, so this equation is going to give me A sine Ka is equal to B 1 minus cosine Ka e to the I Qa. And wherever I see A times sine Ka, I'm going to write this, and B's will cancel. Good. This minus K e to the minus I Qa times A sine Ka. Is my A sine Ka correct? A sine Ka is B. Okay, this is where I messed up. Here's the problem. Okay, so I am trying to solve this one, right? So this is incorrect. Okay, now I found the problem. So this is A sine Ka is going to be B so first is the problem. Here's the problem. So there is like a parenthesis here, right? Because I am, okay, right? We are trying to put the boundary condition. This is e to the I Qa, A sine Ka plus B. There's like a parenthesis. So this is going to be B times e to the I Qa. Now this is A sine K minus B cosine Ka. And this is A sine Ka. Okay, now this is correct. Now wherever I see this, okay, I can also take it like B, like that. And now I think hopefully it will work. And let's see. So this is A sine Ka. I don't want to take it, I just want to take this piece. So this is the first one. So this is cosine Ka minus B sine squared Ka. Let me be careful with my parentheses. Plus K times A sine Ka, which is this, is equal to this thing. And now I will cancel B's, 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 and B's. This K is going to come here. So this is K, this one, and I'll distribute this inside. So this is, let's open up. So this is minus plus, so that I don't miss this one, and this one is minus 1 minus e to the minus I Qa cosine Ka times cosine Ka plus, actually I can do even better. So I can do it like this. So I can do this minus, so this, I want to move this here and here, and I can erase this one, and I can do it like cosine squared. So erase this one, and there's cosine Ka. Okay, and this is cosine squared plus sine squared. This is going to be 1. So this is 1, and I think I don't need this one anymore. Now this is distribute, so this is minus cosine Ka, so this is plus e to the minus I Qa plus e to the I Qa minus cosine Ka is equal, okay, this is minus minus, I'll write minus 2 of these, and so this is equal to this part, and this is sine Ka over K, and this one is cosine 2Qa, so this is 2 cosine Qa, cancel these 2's. Okay, not bad. I mean, I failed a couple of times, but things clean up. And finally, okay, so this is the final result. I'll take this cosine the other side, and I'll leave Q part by itself, so this is like that. So this is plus. Good. Yay. Let me check if this is correct. This is Qa cosine Ka m alpha over h bar square. Yes, this is correct. And how do we solve this equation? Suppose, right, somebody give this equation to you and you need to solve it. So let me put this equation in dimensionless form. Let's define like Q tilde is equal to Qa, K tilde is equal to Ka, and this thing alpha tilde is equal to m alpha over, okay, I need to put A here and A here, m A alpha, so this is m A alpha over h bar squared, so this is alpha tilde, and E is equal to h bar squared K squared over 2m, right? We defined it here. This is our E, and I will define E tilde to be K tilde squared. Okay, there's some E is also proportional to K squared. Then the equation we need to solve is cosine Q tilde is equal to cosine K tilde plus alpha tilde sine K tilde divided by K tilde. And we of course solve equations like this. We cannot solve analytically, we need to solve it graphically. So this is, let's call it f of K tilde alpha tilde, and I will plot alpha tilde, and I know this alpha f, right, is equal to cosine, and it has to be between -1 and +1 because this side is between -1 and +1, and whenever this is satisfied there is a solution, whenever it is not satisfied there is no solution. So let's do this. So f of, okay, I need to magnification, maybe something like this is so this is K and alpha is equal to, what is that, cosine K plus alpha times sine K over K, sine K over K, and let's plot f K for alpha is equal to, let's say, 1, and K is what? K is 0 to 10, something like that. Now let's put also this, right, boundaries are like -1 to 1. Let's also put this and see where we have the solution. So this is -1 +1 and this. Okay, good. So this is telling us the solution. Let's increase alpha. So this is 5. Let's increase alpha to, I don't know, 10. Something like that. You can see solution. I can also increase the range of k. And now let me take this piece and tell you what it means. So this is f, this function, right? And this orange is +1 and blue is -1. And whenever we are here, right, there's like a solution. For example, here there is like a solution. And here there is like a solution from here to here. There's a solution here to here. And here to here. And like here's the solution, here's the solution, here's the solution. And what is this? So this is k, and k is proportional to square root of E. Then there's like a energy band here, right? Solution, and there's no solution. And here is solution, here is no solution. And if I invert this, right, I can think about this like this, energy axis. So this is E, and there is a domain of energy where I have solution of Schrödinger equation. So this is what we call energy band. And there is like a gap. So there is like a gap. So here's the gap. There is no solution here, exactly like quantized levels. But quantized levels, you can see, rather than a single level, I have a band of energies. There's like a gap. There's like another energy band. There's another gap, another energy band, and so on. And we can actually do better than this and see. Okay, let me also do this because I think this is nice. So we can actually do better than that. There's something called parametric plot, and let's plot this thing, right? So what I want to do is like, normally what we should do is like for given k, right? For given q, we need to find k. That's the problem. But for this, for given q, finding k is difficult. This is like a complicated nonlinear equation. It can be done, but there's like a simpler way. We can solve this equation for given k, find q, right? It's the same thing. But the second one is much easier. And how do I know this? Like I can just invert this. So this equation. And I can just, I solved it. So this q is cosine -1 of this thing. And now what I'll do is for each given k, I'll find q, and and whenever you give me k, I know E, and E is k squared. So give me k, I'll calculate E by squaring it, and by using this equation, I'll find q, and I will plot q versus E. So that's what I want to do. So let's do it. So this is q is cosine, it's like arc cosine of f of k. Let's say alpha is, I don't know, again 10, or like let's keep it like this. And so this is my q, and for this given k, energy is k squared. Oops, not here, outside. So this is k squared. I think I need to close this. So this is k squared. And now I'll put some k, I don't know, 0 to 10. Good. And here I also need to do aspect ratio. Okay, aspect ratio 1. Okay, good. And the problem with this solution, right? Cosine is even. For every plus q, minus q is also, right? Because cosine of q is equal to cosine of minus q, I can also incorporate that easily. Like I can say, take this solution and duplicate it. I will put comma, and I will put just a minus here, and I'll do this here, right? So this is very nice. So what is this? So these are, okay, this is Q, so this is E of Q, and you can see there's like minus pi over A to pi over A. So this is what I called first Brillouin zone, and I have here the first energy band, and there's like a forbidden region here, there's like a second band, there's another gap, and third band, and so on. Good? So we solved the Schrödinger equation. That's what we did. And last thing, and I'll after that give you a break. We have something like this, right? So this is energy band, and we went from k squared to something like that, a little bit more complicated. And the question is, how many points do I have here? Right? This is actually continuous, but we know how many q points I have because I just calculated it here, right? So q, right, for n sides in the real space, I have n points in the q space, right? This goes from n goes from minus n over 2 to plus n over 2 plus 1 and minus 1. So there is n points here for each band. So there's like 1, 2, 3, dot, 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 n points. And I have n atoms. And if each atom gives me 1 electron, right, each point can accommodate 2 electrons, I'm going to fill half of this band. Something like that. So this is 1 electron per atom. And this is what we call half filled. And because for every electron here, there is like available energy here, electron can just jump and it can increase its energy. If it can increase its energy, it can conduct. So that is what we call metal. Whereas if we have, for example, 2 electrons per atom, right? Now I need to fill it all the way to here, because each point can accommodate 2 electrons, but I have 2n electrons. And now here is filled electron, there is now a gap here. And if this electron wants to move, it needs to increase its energy, but there is nothing to move, right? There is no place to move. So this is 2 electron per atom, and this is insulator. Okay? So that's how we understand metals and insulators. Whereas free electron theory only tells us everything is metal. Once we put the periodic potential, we also have insulators. Of course, there are also other things. Like if you want to understand semiconductors or semi-metals, you can use exactly the same theory, but you need to go to physics 409 for that. Okay? And as an exercise, okay, we solved the Schrödinger equation, we found the energy. As an exercise, we actually solved the problem, you just need to plug it in, find wave functions for each band and Q and plot in unit cell and see how it looks like in the Dirac comp, like here. Okay, so what is the behavior of wave function? Good. Any questions? I mean, calculation I know is a little bit ugly, but the principles are exactly the same, right? We didn't use any new principle other than this Bloch condition. And in the second hour, I will explain where Bloch condition comes from, and it's going to be, promise, much more entertaining. Good? Okay, let's take a 5-minute break.